Previously, we looked at what happens to the Fibonacci numbers when you take ratios of successive terms. So, let us look at the Fibonacci numbers again, the Fibonacci sequence. So, here is the result we proved, that limit of fn plus 1 over fn exists and equals this special number which we call the golden ratio 1 plus square root of 5 by 2. Okay, so what we will do is let us try and analyze this a little bit more. Where did this number sort of come from? If you recall, this turned out to be the root of the following quadratic equation. So, when we attempted to find the possible value of the limit, we were naturally led to this quadratic equation x squared minus x minus 1 equal to 0, and the roots turn out to be 1 plus minus square root 5 by 2, just using the quadratic formula. So, the positive root is the limit of the fn plus 1 over fn. So, let us just call these roots alpha and beta. 1 plus square root 5 by 2, beta is 1 minus square root 5 by 2, and as we saw, this is approximately 1.6, this would be minus 0.6. So, it is sort of approximately. So, of course, more decimal digits there. Okay. Now, these numbers alpha and beta are both solutions of this equation, that the equation x squared minus x minus 1 is 0. So, what does that tell us? It tells us that alpha and beta themselves satisfy the following equations: alpha square minus alpha minus 1 is 0. In other words, alpha square is equal to alpha plus 1. Likewise, beta squared minus beta minus 1 is 0. So, beta squared equals beta plus 1. Now, here is the interesting thing we can do with this. We multiply both sides of this equation by some power of alpha. So, let us say we multiply both sides of this equation by alpha power n minus 1, okay, where n, I will assume n is at least 1. What does that give us? It tells us that alpha to the n plus 1 equals alpha to the n plus alpha to the n minus 1. Okay. Likewise, for the beta, you conclude beta to the n plus 1 is beta to the n plus beta to the n minus 1. Now, this sort of reminds us already of the Fibonacci recurrence. So, it seems to tell us that if you take the sequence alpha power n, so consider the following sequence just like the Fibonacci, except these are all now real numbers. So, consider the sequence 1 alpha alpha squared and so on. So, maybe we should give these names. So, let us call a n to be alpha power n. Okay, n goes from 0, 1, 2, 3, etc. In other words, I am looking at the sequence 1 alpha alpha squared, powers of alpha. Then these powers of alpha actually satisfy the same recurrence as the Fibonacci numbers, okay, because the n plus 1th power of alpha is equal to the nth power of alpha plus the n minus 1th power of alpha. Okay, the same thing holds for the betas as well. So, if you call this sequence Bn as the nth power of beta, then again beta Bn plus 1 is Bn plus Bn minus 1. So, what this seems to tell us is that the Fibonacci is of course maybe the most famous example, but there are lots of other sequences which sort of arise naturally. These are all sequences of real numbers, and they also satisfy the Fibonacci recurrence. But the interesting thing about these sequences, which we do not yet have for the Fibonacci, is that we have an actual formula for the nth term. So, I can actually write a formula which tells you what the nth term of the sequence an is, right. I actually tell you a formula which you can just use to calculate the nth term in one shot without following the recurrence term by term, right. I do not need to start with the 0th term and then 0 and first term, then compute the second using them, the first two guys, then compute the third from the previous two terms and so on. I can just compute the nth term directly in one shot because I have a formula for the nth term. So, these two sequences A and B have the special property that there are direct formulas for there exists formulas for the nth term, but they actually satisfy the same Fibonacci recurrence. Now, that sort of leads us to ask the question if we can somehow also find a formula for the nth term of the Fibonacci sequence. Okay. So, that's the question we will consider. Is there a formula for the nth term of the Fibonacci sequence now? Okay. So, to do that we will so the answer turns out to be yes, and to do that we will use these two sequences, the powers of alpha and the powers of beta, as some sort of auxiliary step. Okay. So, observe that an and bn actually are sort of very primary building blocks for sequences which satisfy the Fibonacci recurrence. So, what do I mean by that? So, here is my consider the following sequence. So, I am just going to write this as maybe a function of n instead of as a sequence. So, consider the following function, its value at n is some multiple of an. So, some multiple of alpha power n plus some multiple of the other sequence bn, okay, where a and b are some fixed real numbers. So, where a, b are fixed real numbers. Okay, so, I have defined a new function for you. I have fixed coefficients a and b, and as n varies, I am just going to take a multiplied by alpha power n plus b multiplied by beta power n. So, this is sort of a very standard and common technique in math. Once you find two interesting solutions or sequences which satisfy the Fibonacci recurrence, you sort of try to take linear combinations of those. So, that is sort of what we are doing here. Again, something which you see a lot in linear algebra. For instance, you take linear combinations of vectors. So, here is our function f of n. Observe that this function also satisfies the Fibonacci recurrence. So, this is also true because a and b are just constants, and you can just collect term by term. So, observe that this is true. So, we have constructed yet another sequence or function which satisfies the Fibonacci recurrence. Okay, so, this is for n greater than or equal to 1 now. Now, the question is the following: can we somehow find constants a and b such that this function f of n, its values will exactly match with the values of the Fibonacci sequence? So, that is the problem we will try and answer. Question: can we find a, b real numbers such that this value of f of n turns out to be the nth Fibonacci number f n? This is for all n greater than or equal to 0. Okay. So, what is it that we will want to do? We, at the very least, we need to do the following. The Fibonacci numbers start, the 0th and the first terms are both 1, right. So, what we want is the following. We want i.e. we want f0 to be the 0th Fibonacci number, f1 to be the first Fibonacci number, f2 to be the second Fibonacci number, and so on. Okay. But the first and important observation here is that it is actually enough to ensure that the first two terms match. If we can somehow ensure that f0 and f1 are equal to the 0th and first Fibonacci numbers, then that automatically implies that all the other equalities will also hold. Okay. So, this implies that all the other equalities hold, and why is that? Because observe, the function little f also satisfied the Fibonacci recurrence. So, the n plus 1th term would have been just the sum of the two previous terms. right. So, once the first two terms of Fn are both 1s, the next term is forced to be a 2, the next is forced to be a 3 and so on, because the recurrence is the same as the Fibonacci recurrence. So, all we need to do is somehow ensure that the 0th and first terms match, and so that is really going to give us two equations. So, let us write what those equations are. So, recall f of n was a alpha n plus b beta n. So, f0 is a plus b, f1 is a alpha plus b beta, okay. And so, I want this to be 1 and this to be 1. And now we have to solve for a and b, right. Alpha beta are of course known numbers. So, how do we solve this? Well, we can just eliminate one of the variables. So, two equations in two unknowns. So, this tells us that a is obtained by, so you multiply the first equation by alpha and subtract, that will give us b rather than a. So, let us find b first. So, b would just be beta minus alpha. So, I have 1 minus alpha by beta minus alpha. Okay. So, I just multiplied the first equation by alpha and subtracted the first equation from the second. Likewise, I can multiply the first equation by beta and subtract. So, when I do that, I will get 1 minus beta over alpha minus beta. Okay. So, I managed to find what these two numbers are, and in fact, here we know what alpha and beta actually are. They are they are 1 plus root 5 by 2 and 1 minus root 5 by 2. So, you can actually expand this out, substitute, and here is what you find. You find that a is actually a is 1 plus root 5 by 2 root 5, and b turns out to be 1 minus root 5 by minus 2 root 5. Okay. So, a is nothing but alpha by root 5 and b is beta by minus root 5. So, minus beta by root 5. Okay. So, we plug this back in to get our final formula for f of n. This is a times alpha power n plus b times beta power n. So, that is just 1 by square root 5 alpha power n plus 1 minus beta power n plus 1. Okay, and observe that this is in fact going to equal the Fibonacci, the nth Fibonacci numbers. So, the claim is that, so finally here is what we have proved. Theorem, this is sometimes called Lamé's formula. So, this is called Lamé's formula, which gives us a formula for the nth Fibonacci number. It says Fn is 1 by square root 5 alpha power n plus 1 minus beta power n plus 1. And observe, we proved this by just checking the first two terms, that if you plug in n equal to 0 and 1, the left hand side and the right hand side match, and then we know that both sides satisfy the same recurrence relation, right, same 3-term recurrence relation. Every term can be obtained from the two preceding terms. So, the left and the right hand sides will grow in the same way. So, they both start at 1 and then every successive term is obtained using the same formula from the previous terms. So, that is the idea of the proof. Okay. So, we have actually obtained a formula for the nth Fibonacci number, and the very interesting thing about this formula is that even though the Fibonacci number is just a positive integer, it is a natural number, the formula actually involves some irrational numbers. So, it is 1 by root 5, 1 plus square root 5 by 2 whole power n plus 1 and so on, minus 1 minus square root 5 by 2 whole power n plus 1. And it is interesting that finally all the square root 5's in this formula disappear, and what you are left with is actually an integer. So, here is a nice exercise. Try to use, say, the binomial theorem to rewrite this. So, here is a nice problem for you to try. Rewrite the formula, the right hand side, using the binomial theorem. so that none of the root 5's appear. Okay, so you actually can see that Fn is in fact a natural number, okay, to remove the root 5's. So, we talked earlier about the limit of the successive terms of the Fibonacci sequence, and we sort of found the limit by an indirect means. We sort of used the fact that you can look at the even terms and the odd terms, and both of them turn out to be monotonic bounded sequences which converge to limits and so on. But now that we actually have a formula for the nth term, the question is, can we more directly compute this limit? So, limit n tends to alpha, n tends to infinity, Fn plus 1 by Fn. Here is another proof that it is the golden ratio 1 plus root 5 by 2. We actually have a formula. So, this is 1 by square root 5 alpha to the n plus 2 minus beta to the n plus 2 by 1 by square root 5 alpha n plus 1 beta n plus 1. So, I will cancel the square root 5's, and let us also do the following. We will pull out the alphas from both numerator and denominator. So, I write it as 1 minus beta by alpha to the n plus 2 alpha to the n plus 1 beta by alpha to the n plus 1. Now, observe that beta by alpha, so recall beta was approximately minus 0.6, alpha was approximately 1.6, and so the modulus of beta by alpha is strictly smaller than 1, right? It is roughly 0.6 by 1.6, and so if you look at this term here, beta by alpha raised to n plus 2. So, what are we doing? We are taking a number less than 1 and raising it to higher and higher powers. So, we know what happens to it as n goes to infinity. If we take beta by alpha to the n or n plus 1 or n plus 2, it does not matter, any high power as n goes to infinity, you are just going to get 0. So, what this means is that when I compute this limit, this term vanishes, this term vanishes, and I am just left with alpha to the n plus 2 by alpha to the n plus 1, but that is exactly alpha. Okay, and recall alpha was exactly the golden ratio 1 plus square root 5 by 2. So, this gives us another proof that the successive ratios tend towards the golden ratio. Okay, that is done. अभी क्या करना है इसके बाद? Okay, we talk about square root 2. So, now that we have found out a nice technique of determining a formula for the nth term of the Fibonacci sequence, we can ask ourselves if we can somehow get this technique to work in other examples. Can we manufacture other sequences and find exact formulas for their nth terms? Okay, so let us look at other recurrent sequences given by recurrences. So, here is one. So, suppose I say my sequence has, so I will call it S, S0 is 1, S1 is 1 just like the Fibonacci, but Sn plus 1 is 2 times Sn plus Sn minus 1. Okay, so, the extra thing here is this 2. So, I am going to say twice the preceding term plus the term before it, and this is for all n greater than or equal to 1. So, here is my new sequence. So, if you write out the first few terms, it is 1, 1, 2 times 1 plus 1 is 3, 2 times 3 plus 1 is 7, 14 plus 3 is 17, 34 plus 7 41, 82 plus 17 99, and so on. Okay, so, here is a new sequence which has the following property, that the recurrence is a bit like in the Fibonacci case, where you multiply by some, you multiply the two preceding terms by some numbers and you add them together. So let's try and use the same idea. So this is one of those situations where you analyze the proof and then see if that same proof idea can be applied to a different situation. So how did we actually prove the formula, the Lamé's formula for the Fibonacci numbers? We said there's some auxiliary quadratic equation that's somehow hidden in the picture. So let's try and find that equation in this case. So if you recall how that equation appeared in the preceding example of the Fibonacci's, we sort of looked at the coefficient of the n plus 1th term, nth term and n minus 1th term, and sort of put powers of, put x square, x and 1 as the three terms there. So let's do the same thing here. So I'm going to get x squared, 2x, 1, and this difference is 0. So consider this quadratic equation. Now why am I doing this? Let's call its roots as something. So let gamma and delta now be its roots. Okay, whatever they are, we'll compute them in a second. But if gamma delta are the roots, then we repeat the same analysis as before. Gamma squared minus 2 gamma minus 1 is 0. In other words, gamma squared is 2 gamma plus 1. Likewise, delta squared is 2 delta plus 1. And by multiplying by some suitable power of gamma, multiplying by gamma to the n minus 1, you conclude that this equals 2 gamma n plus gamma to the n minus 1. Okay, in other words, the sequence of powers of gamma, if you look at 1 gamma, gamma square and so on, that satisfies the given recurrence. Likewise, delta power n plus 1 is also equal to 2 delta power n plus delta to the n minus 1. Okay, so somehow gamma power n and delta power n are two such sequences. So like we did earlier, we form a linear combination of those two. So let's consider say new sequence f of n to be some multiple of gamma n plus some multiple of delta. Okay, so far we are just copying the same analysis as before for all n greater than or equal to 0, where you fix some real numbers a, b. Okay, and now the question is, can we somehow find a and b such that this, so the goal now is to find constants a, b such that f of n will exactly match with the given sequence Sn for all n greater than or equal to 0. Okay, and again, like before, it is enough to ensure that these two match in the beginning, that f of 0 matches and f of 1 matches, because f satisfies the same recurrence as the SIs, because f of n plus 1 is again 2fn plus n greater than or equal to 1. Okay, so same reasoning, exact same reasoning. So in this case again we have to solve these equations, but before that let's just see what gamma and delta are. They were roots of this equation, x squared minus 2x minus 1. So let's just use the quadratic formula again. What are the roots of this equation? So it's minus b plus or minus square root b squared minus 4ac. So b squared is 4 minus 4ac is 8 by 2. So that is 1 plus or minus square root 2. Okay, so here the two roots are 1 plus root 2 and 1 minus root 2. So let me do that. Let me call gamma as 1 plus root 2, delta is 1 minus root 2. Okay, so again we can find a formula for the terms here. You can solve for a and b. So let me just quickly write those equations out. So let's write this first equation. F of 0 is 1, tells me that a plus b is 1. F of 1 is 1, tells me that a gamma plus b delta is 1, and you have to solve these equations. So here's what we get if you do this. So, please do it on your own and check that this is in fact what you get. Both A and B turn out to be half in this case. Okay. So, what that means is that my formula for the sequence, so my conclusion is the following, that f of n is just given by half of gamma n plus delta n. Okay, for this for all n greater than or equal to 0. Now, and of course that is equal, so this coincides with the given sequence Sn. So that is our final conclusion. Okay, so same reasoning that we did for the Fibonacci case. Now here's the interesting corollary. Like we had in the Fibonacci situation, we can ask what do you get if you now take successive quotients of this sequence Sn. Well, the answer is we just use the formula. It is half of gamma n plus delta n. So it's Sn plus 1, so gamma n plus 1, delta n plus 1, gamma n plus delta n, and the same calculation as before tells us that the halves can be cancelled. I can pull out gamma to the n plus 1 from the top and gamma to the n from the bottom. So I get this. And again delta, remember, is 1 minus square root 2 and gamma is 1 plus square root 2. So it's 1 minus square root 2, which is approximately minus 0.414, etc. Gamma itself is 1 plus square root 2. So that's 2.414. And again here delta by gamma is some real number of modulus less than 1, and so these two go to 0 as n goes to infinity. So this is the limit as n goes to infinity is 0, limit is 0. And so the final answer is gamma here again, just like we had in the other Fibonacci situation. The root gamma is what you get, and what was gamma? It was 1 plus root 2. Okay, so here's an interesting corollary. If you were trying to compute the value of square root 2, for example, what we have manufactured is a sequence of rational numbers which converges to 1 plus root 2, but we can always subtract 1 from it. So here's an interesting statement, if you will. If you looked at that sequence that I wrote out, the original sequence, here it is. So you take this sequence and you just take successive quotients. Okay, so I take 1 over 1, 3 over 3, and so on. So what this tells us is, if you look at the original sequence, here it is, and you take successive quotients. I take the second term divided by the first term, so which is 1 by 1, 3 by 1, 7 by 3, 17 by 7, and so on. What you get is a sequence of rational numbers which has a limit 1 plus square root 2. So if you were trying to say approximate square root 2, what you could do is just take each of these rational numbers and sort of subtract 1 from these. Okay, so you would get a sequence of rational numbers converging to square root 2. So this is one way of maybe getting some quick approximation to the square root of 2. So here's a nice problem for you. Consider a more general sequence given by a recurrence. Consider a sequence, we will call it T now. So given by the following recurrence, T0 is 1, T1 is 1, and Tn plus 1 is some multiple of Tn. So let's call it P times Tn plus Q times Tn minus 1 for n greater than or equal to 1. Find P and Q such that, so find a suitable choice of PQ such that the successive quotients converges, they converge the sequence, and it converges to, let us say, root 3 or 1 plus root 3. So, something which will enable you to compute the values of root 3 by just taking these rational numbers and then subtracting 1 from them.